I would like to ask some questions regarding the part on love waves. So, okay, so love waves, you can find them at the very small scales, but you can also find them at the seismic geophysical scale. So you've shown us some results at the very small scale, but do you have the knowledge of any similar results as a geophysics scale?
Yes, I must confess I do not know. Now, I was talking about love waves only in the context of these, bound states in the radiation continuum.
Yeah.
So basically, my point was that for love waves, these bound states and continuum do not exist. Or in other words, there cannot be love waves which propagate faster than the bulk transverse waves.
Yes.
So then they ought to become leaky. So that was basically purely theoretical point, but yes, I don't know much about geophysics. I would imagine that the waves that generated by nature, let's say in earthquakes, those would be mostly, let's say, Rayleigh waves or Rayleigh lamp waves. But of course, people in geophysics, they also use transducers, right? So they can generate any waves they want. So I would imagine that they have investigated this. Or even, the acoustic fields generated, let's say, by glaciers. Yes, those could very easily, involve love waves indeed.
Can we go back to your paper? So I think it was published in Journal of Applied Physics. Can we discuss it again? Because, yeah.
You mean this one?
Yeah, this one. So, okay, I'm not sure I fully understand. So, what is the type of wave you consider here?
Well, this is just, the Lorentz oscillator model. This is, in the simplest case, simply light or sound in the medium with the resonance.
Okay.
So let's say this could be just, gas molecules or atoms with some electronic resonance. So that's what, the Lorentz oscillator model describes. But my point is that this is universal. So basically, anywhere you have, an oscillator, oscillators dispersed in the medium, whether it's acoustic or optics, you disperse mechanical oscillators, or you have, microspheres on the surface, and you have the same kind of equation. So here without damping, but if you include damping, it will be a similar system.
But by the way, here, so it's some kind of, perturbed Rayleigh wave equation. So usually the Rayleigh wave equation, you would have this linear slope.
Yes.
Here you have this, this small slope, and you have some kind of hybridized Rayleigh wave.
Yes.
And similar types of hybridized Rayleigh waves have been found, for trees. So you have a soil substrate and you have tree. But here, obviously, not trees. They are like, spheres. And so it's very, very interesting. So you have just a single contact because the sphere touches the surface at a single point, or, the sphere, there is more than one point of contact.
Well, this is not really a point. This is an area, the finite area. So the basically within the Hertzian model, yes, there is of course there is a finite area. Yes.
Okay. And the spheres, they touch each other. They touch the spheres.
They touch each other. No. Okay. So this is the model of non-interacting spheres. The model here is for the spheres that do not touch. Right now, okay. In the experiment, the spheres touch, and moreover, this model only accounts for the vertical resonance, for the vertical motion. But spheres could also move horizontally, and when they move horizontally, they can also rotate. Right? Yeah. So therefore, in fact, there are more resonances. So, and I can show you, perhaps, I have an additional slide. When you do this experiment, when you do more accurate measurements of attenuation, then you find that there are additional resonances. So the strongest resonances is this vertical motion of the spheres, but there are two additional resonances which also interact with the Rayleigh waves. And these resonances correspond to horizontal rotational motion of the spheres.
Yeah.
So there are 3 degrees of freedom: vertical, horizontal, and rotation. Therefore, there are 3 resonances, but they're weaker. And if you look here at the upper horizontal rotational resonances, you see that there is no avoided crossing anymore. So the only thing that happens, there is increased attenuation of surface acoustic waves around this crossing, but the avoided crossing does not happen. And this is exactly what I'm describing. That is depending on the damping and the strength of the interaction. So the interaction is weaker. So we are here in this regime where we have weak coupling and the dispersions just cross. You see? So that's
very interesting. That's very interesting. So for the trees, effectively, as well for the trees, the stronger coupling is with the longitudinal resonance, so with the compressional one. So this is when you have, but for the trees, you have also flexural motion of the tree, coupled with the Rayleigh wave. Okay.
Right. Yes, I think even normally. So this model, this is sort of the effective medium model, which assumes that the resonance has low frequency, such that the corresponding wavelength is much larger than the distance between the oscillator. So that is for the flexural resonances of the trees, because that's low frequency. This will be sort of more applicable.
I did not know this paper. I discovered this paper. It's a fantastic paper with the balls. It's fantastic. I really like to read it. I have other questions. I mean, maybe later on, but I have many questions about your Journal of Applied Physics. I think I need to read it because I'm very surprised. So nobody investigated this before. Nobody touched this.
I mean, this is really very primitive, right? I mean, this is a primitive equation, and this is a primitive investigation. But
but like you said, we use this model for many kinds of wave topics. As soon as
of course,
some locally, strange. Okay, thank you very much. It's a wonderful talk. Thank you so much.
So Alex, just on that note, what is the best way to prove this experimentally? What would you suggest?
So of course, indirect evidence is there. That is, we can see that we have this situation and this situation, right?
But maybe somebody should look for that.
But this particular shape, this interesting shape of the dispersion, I have not seen that. So of course, although this seems like something very profound, but don't forget, this is happening where the system is already sort of a little bit overdamped, right? That is, the lines are broad, right? Yes. So if you measure the real part, then you see this feature, but in an experiment, you won't really see much. So you need to do sort of accurate measurements, and what this requires is that you should be able to tune either the damping in your system or the interaction strength. And this is not easy, right? So you take your system and how would you continuously tune the damping? So if you have a way of continuously tune either the damping, or, people have experimented with magnetic fields, also the contact resonance, but they use magnetic particles, and they use magnetic field to sort of tune things. So maybe you can use it not to tune the damping, but you can also tune the interaction strength, and you'll get the same effect. Yeah. So I think it's possible, but it requires some experimental ingenuity.
I think, Alex, I think it's possible. It is possible that our phonon polariton systems could provide something like this. You can't tune the damping over every possible range, but because you do have coupling to optical phonons that can be extremely strongly damped, I think it's possible that it would be that there may be situations where you could find the right set of parameters.
Yeah, but how do you fine tune a parameter?
Well, with temperature,
you have your system, and you either have strong coupling, then you set this, or you have weak coupling, then you set this.
Yes,
but how do you actually go through the transition and get through this exceptional point?
Yes, I can't promise that it's possible, but because the coupling can be to ferroelectric modes that can be soft modes, the temperature tuning can give you a very strong variation of the damping.
Okay, yes, indeed. Yeah, you can temperature tune. Yeah, that's a good point. Temperature could affect the damping. Yes, indeed.
Yes, yep. I can't promise it, but I think it is possible.
Yeah, by temperature, indeed. Yeah, that's possible.
So, this is Nick Fang. Alex, I really appreciate your comment and insight. Yeah, I think at least for the case of the home port resonators, I have seen the examples of adjusting the damping by using a porous material, for example, at the neck or around the cavity. So that may be a opportunities to fine tune the coupling with the damping term.
No, of course, people do these experiments with exceptional points, but yeah, but more typically, this is just a resonator. So you have coupled resonators, and you can tune damping of a resonator.
That's right.
Not of many resonators dispersed in the medium, from what I've seen.
Mm-hmm.
I have another question, if I could, which is in this case where you showed that you have these elliptically polarized regions of wave vector and then separated by either vertical or horizontal polarizations. I suppose you would say that is symmetry protected. Yes.
Yeah, sort of, but
well, that's why I'm asking, because I'm not quite sure if you would define it that way, and if you would, then my question is it possible to find a non-symmetry protected point?
Yes, I don't really see how it's symmetry protected, because if you consider the total wave field, so this is a sagittally polarized wave. It's just at the surface that it becomes horizontally polarized, right? But everywhere else, if you go away from the surface, this is generally elliptically polarized, and it's polarized in the sagittal plane. And now we have the wave and the liquid, the longitudinal wave and the liquid can also be polarized in the same plane. So I don't quite see how the wave field in the solid and the wave field in the liquid have different symmetry. So it's not.
Okay.
Yeah. So I'm not sure this is symmetry protected.
Yeah.
But this is this is really unique, because indeed for a solid fluid interface, you may have a situation where the field in the fluid is identically zero. With a solid interface, or in optics with a fluid interface, this cannot exist. There should be an evanescent field in the other medium where you radiate or don't radiate. So that's why in optics you need a photonic crystal. It can for a homogeneous slab this cannot be, because if your velocity is faster than the speed of light, then either you radiate or your field is zero. But if you have a photonic crystal, you have then your wave vector has you have multiple. In the block expansion, you have multiple spatial harmonics. You see, and some of these spatial harmonics will have an evanescent field then.
Mm-hmm. Yeah.
because some of them turn out to be below the light cone. Some of the Fourier components of your field. Since your plane wave is now, a sum of many special Fourier components.
Yeah, yeah.
While we're on the subject of this liquid-solid interface, can you explain what you did with the liquid viscosity in these discussions?
No, we assume no viscosity.
No, because otherwise it will radiate, won't it? If it's a
well, there will be loss, but there will be no wave loss. There will be a viscous loss, sure, right? But we are only talking about radiation of waves here.
Okay, so you had in-viscous calculations.
In-viscous, yes.
Okay, that's what I thought. Thanks. In experiment, I don't know if it's a good approximation or not. If it's water, for example. Is it good enough?
I think it's normally it's a good approximation because normally if you have, let's say, Rayleigh wave and you immerse your solid in water, there will be very large. That is, the radiation loss will dominate. It will be much greater than your viscous loss at the boundary. That's actually known. So this is what's studied in acoustic microscopy typically, right?
Well, I was talking about the case where the velocity of the solid is in plane at the surface.
Well, yes, of course there will be viscous loss, right? But there will be also some viscous loss in the solid, right? So
of course, in the solid too.
Always, right? So that is the question: what's dominating, right?
Okay. So you didn't really answer the question. To come back to the Journal of Applied Physics paper, would you do this proof in optics? Or, I mean, Keith Nelson also gave us a hint, but would you do it in optics or acoustics? Please tell me, which one did you mean? Given Keith's hint, would you do it in optics or acoustics? Oh, shouldn't you say anymore because you're in a public location now? I don't think that'll give too much away, will it?
Well, yes. So Keith's suggestion is really not even. Yeah. So you could do indeed sort of phonon polariton or even magnon polariton, right?
Okay. So it's not really necessarily one single answers, optics or acoustics.
In fact, plasmon polaritons would be a real possibility also, because there, of course, you have very strong damping.
You were thinking about optical system then, Keith?
Well, I was only in the effort to think of a system that would have the right kind of intersection in the dispersion and the possibility of sort of tuning the line width.
So yeah, we also can consider, because since we are trying to generate coherent magnons, we can also consider, the interaction of magnons with surface acoustic waves. That's another avoided crossing possibility, and could also be perhaps tuned by something, by external.
Well, we certainly have avoided crossings between magnons and phonon polaritons.
Right. No, that's true, right? And there you clearly have shown that there is, the strong coupling regime and, real sort of hybridization and avoided crossing. Yes.
Yes, and again, we didn't attempt to do anything regarding the damping of of either of the waves, but again, depending on the system used, it might be possible, especially somewhere near a ferroelectric phase transition, to essentially tune the damping.
Right. And your measurement is exactly, your experiment is exactly the right kind of experiment, what I call the scattering experiment, right? Because you can generate your field, inside a sample. By doing that, you impose the real wave vector, and then you measure the response. That will be complex frequency.
Yep.
By the way, at this exceptional point, how many wavelengths does your wave travel before it dies away? I mean, it's almost not a wave anymore at that condition? Is it, how many wavelengths is it going?
Yes, this actually depends on the, you see, there is no definite answer because the damping at the exceptional point is a function of the coupling strength. So you see, it's actually 2 square roots of the coupling strength. That is, if the coupling strength is small, then this exceptional point occurs at low damping. So the low damping situation is in principle possible.
That would probably be easier experimentally, wouldn't it?
Yeah. That would be a big, but very low damped, very sharp resonance. So that's the situation then.
Okay, thank you.
As opposed to, you know, strong, very strong interaction and strong damping. But then, of course, the splitting is also small, right? So at any rate, you have, so at the exceptional point, so really sort of the widths of the resonances, right, are much larger than this distance. So if you just measure the spectrum, then your 2 lines will overlap at this point. But if you measure you need to measure this real and imaginary parts accurately to really get this, you know, the shape.
I think there would be systems where you could quite nicely tune the damping better than looking at soft modes, you know, where, for example, I think you might need very little more than, since at least the kinds of experiments that we've done, they're in thin slabs anyway. If you simply loaded the slab with a liquid with a floppy vibrational mode of the same frequency range as the phonon polaritons, that would be better than a soft mode, because then you would increase the damping, I think, quite dramatically, but not change the frequency. And so I actually think that it would be quite possible to find this. Maybe this is going a little bit toward the example that Nick was suggesting at the very beginning, because but in any event, you could do this at the frequency range where you would have an intersection and tunable damping.
Well, I must confess, I did not expect that this sort of exceptional point topic would generate this amount of interest in the experimental context, because people, of course, have observed exceptional points in other systems. So I thought it just, you know, a curious thing that it is occurring in this, you know, very basic Lorentz dispersion model. But basically, this is equivalent to interacting oscillators. You can the Lorentz dispersion model. You can show that the system cannot be mapped on two interacting oscillators. And with interacting oscillators, I'm sure it has been observed.
So the message today is that, are you trying to say that people who do investigate complicated periodic structures should check their phenomenon doesn't occur in non-periodic structures before they make wild claims? Is that the message? Yeah.
Well, you know, even ourselves in our own investigation, when we try to be careful, right? Oftentimes, there is one slide that I didn't show because I thought I didn't have enough time. I was talking about this, you know, fluid-loaded systems. So there is one slide I didn't comment on, after we completed our investigation, we started looking in the literature, and we found that a similar phenomenon for immersed lamp waves in an immersed plate has been reported as early as 1995. Basically, it was found that there are certain points on the lamp dispersion where lamp waves do not, in an immersed place, don't couple to the surrounding liquid. So, you know, basically the resonances become infinitely narrow nulls in the resonance with curves, you see, and sites and the cause of published experimental non-observance of radiation effects for individual lamp modes. So you see, nothing's new under the sun. But this this doesn't matter, does not mean that you cannot discover anything new. And even that paper that reported, you know, the first experimental observation of embedded states, even though the embedded states existed in the cell phones, it was still a very important paper, right? Because it basically it opened this whole subfield of science and generated a lot of very interesting new results.
Well, also seeing these things help us understand those things better, actually.
Yeah, but it's still useful to, you know, have some sort of historical perspective and know what your predecessors have done.
I think there's an interesting field of research that you didn't touch on today, Alex, which is surface acoustic waves on a crystalline sphere, which has been quite sort of seriously investigated by Professor Yamanaka of Tohoku University.
Yes, this is very beautiful, indeed.
Yeah, and they find various modes that don't diffract on a sphere because of curvature dispersion cancelling out normal diffraction, effects cancelling out diffraction. So I think there's a lot still to be done in that field. They even discovered meandering trajectories like snake.
Yes, I have seen that. Yes, this is very beautiful indeed. Yeah.
Can you spell out the name, Oliver and Alex? I don't know this.
Kazushi Yamanaka, right?
Yeah, Kazushi Yamanaka, yes.
Yeah, you should invite him to speak at your next seminar.
Definitely.
That's
if you
true.
can drop us an email, we would like to invite.
Okay. I'll ask him. Yeah.
It's a he. Okay.
I don't know if he's. Yeah. Anyway, he's around.
Okay.
But one question. I have a stupid question. Okay, for a sphere, obviously, you cannot tile the sphere periodically. So how does this happen? I mean, because the sphere, because of the curvature, because the endpoints, the north and the south pole, what happens there? I mean,
you don't have to go to the north and south pole. You can go around the equator. You see, the stable orbits are often perpendicular to one of the axes. So
okay.
You can avoid the north and south poles if you want to.
The thing is that the sphere is made out of crystal. So it's not an isotropic sphere. It's made of an anisotropic material. So that's what's interesting about that.
Yeah, but the way you pave the sphere, the way, even the way you can pave, you can tile the sphere is already, very interesting. Very interesting.
So if you don't restrict yourself to spheres, you can do something no one's ever even tried. You could put surface waves on a torus, for example. I mean, where would you stop?
Yeah, of course.
You could also see the interaction between something like the breathing mode of the sphere or a torus and these surface waves, of course, this would have an interesting effect in these special regions. It would move them around at least.
Mm-hmm.
I think the title "Surface Waves on a Crystal Donut" makes a good paper.
Yes, it's lovely. Yeah, of course. No, it's lovely. It's lovely. Yeah, of course.
I have to think about that one.
So yeah, on periodic manifolds in general.
Who's going to make the crystal donuts, though? I mean,
no.
It's a bit difficult to polish it.
you can already see the press release.
You might be able to see something interesting even on a conventional isotropic donut, perhaps. Has it been investigated on something?
Not really. No, there's no paper on the surface waves.
Yeah, so I'm sure on spheres and cylinders that has been investigated, but you may be able to find, in non-trivial geometry where something interesting happens.
Yeah, surface waves on an isotropic donut's a good place to start. Yeah. We have a topic. Interesting.
By the way, really, people who attend these meetings, you are strongly encouraged to propose names for, speakers. And yeah, we need names, we need lovely talks such as the talk of today. I mean, this is really nice because you reach out to many different disciplines, and this is exactly what we want to have. I really love this talk today. Thank you so much, Alex.
Yeah, by the way, Sebastian, you and Bogdan are the boss, so you have to decide when to close the session. I'm not going to do that.
I mean, as far as I'm concerned, if you still want to discuss, it's still not a closure. But if you think you don't want to add anything else, I mean, Mr. Chairman, at the end, you're the chairman.
Oh, okay. Well, Alex, do you want to keep? How are you doing, Alex?
I'm still alive. Thank you for asking, Professor Wright.
Okay. Well, I mean, just any more questions? I mean, there's a limit, I guess. I mean, okay, the fact that it's 11:30 in the night in Japan, but that's not really a big deal. That's not a problem. It's still early, really. What time is it in Boston there?
It's nice and early at 10:30 a.m.
Oh, okay. Fair enough. There is some, maybe, I don't know, yeah. Is anybody from the topological acoustics field, or in particular from the topological optics field who's attending, who wants to just comment on how this kind of work might stimulate them or otherwise on their classical periodic structures as opposed to these non-periodic structures which show exactly the same phenomenon. So this is the big question, because maybe, Alex, you can tell us, is there a magic formula that you can apply to a structure, whether it be periodic or not, that will test quickly whether it shows this effect or not? Each of these different effects you showed, for example, Veselago lens, or exceptional point, or non-diffractive propagation. Is there some way do we have a very, very quick way to test in any case, whatever structure you have, whether it occurs or not? I mean, theoretically, I don't really mean just experimentally. Of course, experimentally, you can always test. Is there some signature that gives you what will make a Veselago lens? You know, you can have it made with things with holes that are periodic. You can have it with a plate that just changes thickness. It's surprising. I mean, it's so surprising. So it means that we could find it in other systems that we didn't even think about. What is this trying to? What is this?
Yeah, for the Veselago lens, yes, the recipe is known. All you need is negative group velocity. So
okay,
a system that will give you negative group velocity will give you that. So
okay, so your big message today is just look at the dispersion relation. Is that the message?
I don't know. Not
the
sure.
Dispersion relation will tell all. Is that correct?
By the way, I did not talk about anything topological, and indeed, I don't know an example of a phenomenon in the topological acoustics that has been well known for decades. But you know, there is at least one example of non-reciprocal acoustics that has been well known, and this is when the sort of when you communicate and there is wind, then when you speak downwind, your recipient will hear you better than when you speak in the direction upwind. So this is a non-reciprocal acoustics phenomenon, and I saw it described in the big Soviet encyclopedia, printed in sometimes in the 1960s.
So non-reciprocal acoustics, all you need to do is go out on a windy...
Non-reciprocal acoustics, yeah. So non-reciprocal acoustics has been some non-reciprocal acoustics phenomenon have been on for decades indeed.
Just go out on a windy day and try and call your friend upwind or downwind.
Right.
Yeah, fair enough. I would say that your talk is it's a kind of, what shall we say? It's like a whistleblower or something like that. I mean, it's a kind of brave thing to do, I think, to go against the grain of the major trends of the day. Perhaps we should all take note and imitate you. Yeah. But not, I mean, it's good to be caught along by the trends because you make friends and you you discover new physics. But sometimes it's good to sit back and make sure you didn't miss the 100 year ago or whatever phenomena, and check it hasn't already been done before. That's maybe the message of today. Is that right?
Okay. This is Nick again. I disagree. I felt that this is a good reflection. It outlined many necessary conditions. It may not be all sufficient, or I think in terms of say comparing, say, like the general theory behind this, maybe it's just more of a different way of classification, not necessarily a completely say a contrast of different approaches.
Thank you for that comment. Yeah, so it's very good. Anyway, I think everybody was very stimulated, and it's not my job to say this. Bogdan and Sebastian normally say this, but please, I'm sure they want you to come along more regularly and ask questions, and yeah. And as I'm not a good chairman because I didn't ask the people who are attending to ask a question, but I mean, it's a bit mean to mention a name of somebody you know who was on the list who hasn't shown their interest to ask a question, and say, how about asking a question? You do that inside your research lab, but so it's quite difficult because online is different from offline, and people need to, yeah. Some people hate online, so you can't force people to ask questions. But anyway, I hope that the general what shall we say? Yeah, that everybody feels relaxed enough to butt in and ask what they want at any time. And please, Alex, come and attend some of these meetings more often if you can. So I think, I don't know, I mean, there's a finite time and people want to go and have their lunch or their dinner or go to bed or something. So perhaps we can call it a day. Would you allow me to close the session, guys? And guys and girls, I should say, but guys is a word which applies to both. So it's okay in the US. So will you allow me to close the session? Yeah? Okay, yeah, thank you. So thank you very much. And great. It was enjoyable. Yeah, I'm very impressed. Yeah, thank you, Alex.
Right, thank you.
Yeah. So bye for now, everybody. Yeah.
Bye, guys. And next week we have Daniel Penel from Femto on neural network, by the way. It will be really exciting. Just have a look at the agenda. Thank you so much, Mr. Chairman. Thank you so much, everyone. It's fantastic.
You're welcome. Thank you.
Bogdan, it's in the box. All is in the box.
Thank you. Yeah.
Yeah, good. So